In modern disaster response, automated quadcopters are capable of mapping damaged structures across thousands of homes in minutes. But the physical scale and chaos of a high-stakes disaster zone place extreme operational demands on these vehicles. The engineering hurdle in these environments is the concrete and steel itself. Satellite GPS signals cannot penetrate this dense debris to reach a receiver. Without satellite data to provide absolute geographic coordinates, the vehicles have no reference for their global location. To navigate the rubble, a swarm must construct a localized geometry from scratch, relying on a continuous exchange of high-frequency data to maintain its spatial awareness. Standard visual odometry systems, like cameras and LiDAR, struggle here. Thick smoke, dust, and dynamic lighting effectively blind optical sensors. Narrow-band radio systems like Wi-Fi and Bluetooth also fail to fill the gap, as they cannot provide the centimeter-level precision required to maneuver through tight corridors. Coordinating a fleet inside these structures requires a specific engineering stack: ultra-wideband radio physics, nonlinear state estimation, and decentralized mesh protocols. Navigating these chaotic spaces depends on the high-frequency calculation of the drone's position, velocity, and orientation, the variables that define its mathematical state. This diagram illustrates a primary obstacle for indoor navigation: multipath interference. When standard radio signals are emitted indoors, the waves bounce off walls and objects, overlapping and corrupting the distance measurement. Engineers bypass this by utilizing the ultra-wideband spectrum, transmitting across a wide range between 3.1 and 10.6 GHz. Because of this wide bandwidth, the transmission consists of incredibly short pulses. This allows a receiver to separate signals chronologically. The direct, line-of-sight pulse hits first, while delayed, reflected pulses arrive later and are mathematically filtered out. This time-domain resolution makes the system resistant to the multipath attenuation that typically cripples Bluetooth and Wi-Fi. Manipulating the physical properties of the radio pulse is the prerequisite for accurate indoor localization. Here, two independent drones, Node A and Node B, use time-of-flight math to measure the distance between them. They utilize double-sided two-way ranging, exchanging 3 packets: a poll, a response, and a final message. The equation isolates variables representing the internal processing delays. The internal processing delays of each drone's hardware cancel each other out in this 3-packet exchange, leaving only the pure propagation time. Operationally, this means the drones do not need perfectly synchronized internal clocks to achieve centimeter-level ranging. However, this topology has a scalability bottleneck. Packet overhead increases exponentially as drones are added. A swarm of 20 drones would generate an overwhelming web of signals that saturates the available bandwidth. Supporting larger fleets requires an alternative topology: time difference of arrival. Time difference of arrival requires fewer packets, providing high scalability, but it trades efficiency for a strict requirement: all nodes must maintain perfect clock synchronization. Designing a swarm requires calculating the trade-off between unsynchronized reliability and synchronized efficiency based on the network size. This graph plots a drone's true trajectory, the smooth curve, overlaid with raw radio measurements. When walls block the line of sight, the hardware produces erratic data. To compensate, the flight controller pulls data from the inertial measurement unit, which provides high-frequency readings of acceleration and rotation. But the IMU suffers from integration drift. As you can see, the data starts perfectly aligned with the trajectory, but the accumulation of microscopic errors causes the curve to veer off into open space. The mathematical engine that resolves the conflict between drifting inertial data and erratic radio data is the extended Kalman filter. The filter executes a 2-step process. The IMU provides a short-term prediction of the drone's state, and the system demises the radio points as an absolute update, pulling the drifting line back onto the true trajectory. Multi-sensor fusion is the only way to maintain autonomy. No single sensor can survive a highly unstructured environment alone. Transitioning to multi-agent swarm intelligence requires shifting the entire coordinate system. Instead of referencing static wall points, the drones act as mobile anchors for one another, creating a floating coordinate frame that moves with the fleet. All state estimation is capsulated on the edge via individual flight controllers, removing the need for a central command server. To coordinate movement, these flight controllers utilize bio-inspired consensus algorithms that rely on peer-to-peer distance vectors. Collision avoidance and formation changes are executed purely through mathematics, keeping those distance vectors within predefined thresholds. Swarm intelligence is an emergent property created by locking decentralized nodes into a shared relative mathematical space. When we return to the collapsed building and view the environment through the data layer of the active swarm, the mechanics of the operation become clear. The onboard IMUs run high-frequency predictions, while the radio transceivers fire packets through the concrete dust. If the swarm detects an impassable obstacle, the nodes mathematically recalculate their geometric mesh, bypassing the debris without losing formation. The capability to map structural damage autonomously is the direct output of rigorous, packet-level state estimation. The hardware transition to next-generation modules is already underway, tightening the baseline accuracy of the entire network. On the software horizon, deep learning algorithms are being integrated directly into the flight controller to recognize and reject corrupted radio signatures. Future inter-swarm protocols will allow multiple independent fleets to merge their coordinate frames into a single massive theater map. In GPS-denied environments, the functional limits of artificial intelligence are defined by the physics of the radio frequency spectrum. Mastering the hardware layer provides the high-fidelity data that enables stable, collective flight.